All right, in this video, we're going to be looking at the common ion effect, or how common ions affect the equilibrium constant. And we have a multiple choice and a short answer. So in this multiple choice, how many moles of NaF must be dissolved in 1 liter of a saturated solution of PbF2 at 25 degrees Celsius to reduce the lead concentration to 1 times 10 to the negative 6th molar? And we have a KSP of PF2 at 25 degrees Celsius is found to be 4 times 10 to the negative 8. Okay, it seems like a lot of words, not really sure exactly what to do. Just understand that we're looking at equilibrium, and we need to write out the equilibrium constant. So KSP for lead nitrate, or it's not lead nitrate, lead fluoride is going to be Pb plus 2 F minus squared. Don't forget the squared. There's 2 ions here for every 1 lead. So when we write out the reaction, right, we would have 2 fluoride ions. So make sure that it's squared in your KSP. Okay. We do know the KSP, so I could replace that KSP for 4 times 10 to the negative 8th. And what are we looking for? We're looking for how many moles of NaF we need to figure out how much it will fit in the solution. So the one ion that we have in common with NaF is the fluorine concentration. So we actually just need to figure out what's the fluorine concentration, and how much do we need to solve for that. So we need this concentration, and we do know the lead concentration. They give it to us there that they want it to be at. So let's plug that in. 1 times 10 to the negative 6th. And we're looking for the F minus concentration. So to solve for that, I'm going to divide each sides by 1 times 10 to the negative 6, 1 times 10 to the negative 6. That's going to give me that the F minus concentration squared is equal to 0.04. All right. Now, I need to know just the concentration of the fluorine and not it being squared. So I'm going to take the square root of each side. And if you do that, you find that you get 0.2 as your answer here. So the concentration of the F minus is 0.2. And remember, that's in molarity. We got to figure out how many moles we need of that. Luckily, this question makes it really nice and easy, and a lot of the AP questions do that. It's a 1 liter solution, so you just have to divide by the 1 liter, and you figure out how many moles you need, which is 0.2 moles. Luckily, that's an answer choice, so we must have done it right, and D is the right answer. So that's how you solve that one right there. Looking at this short answer question, answer the following questions about the solubility of AgCl solid or silver chloride. The value of KSP for silver chloride is 1 times 10 negative 10. Part A, and I'm going to do it kind of like down here, just away from everything. So part A, we want to calculate the value of the Ag plus in a saturated solution of AgCl. Okay, so we have everything we need. We need to know that the KSP for this is just Ag plus and Cl minus. And they give us the KSP, so we should be able to easily solve for our silver plus concentration. If we know this is 1 times 8 times 10 to the negative 10, that's essentially going to be x squared. The concentrations are going to be equal for every 1 molecule of AgCl. It breaks down into 1 ion of each. So then I just got to take the square root of each side, and I'll find that my Ag plus concentration is going to be equal to 1.3 times 10 to the negative 5th molarity. And that's it. That's all you got to do to solve part A. Pretty simple. Part B, number 1, we're looking to calculate the molar solubility of AgCl solid in seawater. And B tells us the concentration of Cl minus in seawater is 0.54 molar. So that seawater, that Cl minus ion that it has is a common ion for that AgCl solid. So what it's saying is, like in this first example, we just put silver chloride in pure water. So it's just going to break down and we'll get a concentration of 1.3 times 10 negative fifth. But if we were to put this solid salt into seawater, there's already chlorine ions in it. It's affecting the ionization of that AgCl, so not as much is going to come out. So what do? We're going to put our KSP still to, so this is part 1. Our KSP, which is 1.8 times 10 to the negative 10, that's great. But we don't know, or we're looking for the concentration of Ag+, but instead I'm going to put 0.54 as the solution concentration for my Cl minus. So that's my Cl minus concentration. I get that right here. So now I'm going to solve for the Ag+ concentration with that chlorine solution right here. Now, what I should put also is plus X, plus that ions that's going to go into this one, but it's going to be quite negligible to this 0.54. Look at this. This is 1.3 times 10 to the negative fifth. So if I were to add like 1.3 times 10 to the negative fifth ions that might come out, right? That is nothing compared to 0.54. So I'm going to consider it negligible and just put the 0.54 there. Okay, to solve it, I'm going to divide 0.54 on each side. That's a concentration, 0.54 concentration. And I'll find that my Ag+ concentration is now 3.3 times 10 to the negative 10. So look, this is the concentration in seawater of the Ag+. It is much smaller. It's 5 times the power level compared to in regular water. You're going to get a whole lot less ions of silver in the seawater. And that's because there's already so much chlorine in there that not a lot of it's going to dissolve out. Okay, part 2, it says explain why AgCl is less soluble in seawater than in distilled water. You should say something along the lines like the increased chlorine concentration, so increased, this is part 2, Cl minus concentration decreases the solubility of AgCl solid. And you probably want to say something like, because this chlorine ions are a common ion in AgCl. I should say the chlorine ions in the salt water are a common ion in AgCl. So to do that common ion, and that's really the key word, talking about how they have common ions, is going to ruin that solubility for the silver chloride. Okay, hope that was helpful.